Recently, Wi-Fi has been a preferred choice for the last mile delivery in IoT networks, mainly due to the following reasons. First, Wi-Fi provides a higher data rate than technologies such as Zigbee and Bluetooth. Also, Wi-Fi operates in an unlicensed spectrum, hence the cost of deployment of Wi-Fi systems is relatively lower compared to technologies such as LTE or 3GPP. Lastly, most residential, enterprise or industrial buildings already consist of an established Wi-Fi network. Hence, these Wi-Fi networks can also be used for IoT systems, reducing the cost of deployment further. Monitoring Wi-Fi networks are very important due to several reasons. For example, as malicious attacker can easily inject packets into the network or generate a DDoS attack and reduce the efficiency of the entire system. Also, to characterize and analyze the wireless environment to look for potential improvements via data-driven and machine learning techniques. And in reality, the possibilities are endless. Several tools such as EthTool and SNMP provide a platform for monitoring and collecting network statistics that can collect measurements every few seconds and can be utilized for applications such as channel assignment and access point selection. However, high rate real-time measurements are essential in order to interpret the highly fluctuating network dynamics in various other applications. For example, making per packet scheduling decisions or to identify the power state and energy patterns of the devices in the network. Another application where real-time measurements of a network are essential is adjusting the listen interval or the target wake-up time. Listen interval allows the Wi-Fi stations to wake up for only certain beacons, thus saving energy, and target wake-up time enables frame transmissions between two stations at scheduled intervals and switching to low power dose state in the remaining time. Linux mainly consists of two components, which are the kernel space and the user space. The kernel space is the protected memory space, which mainly consists of operating system and the networking stack, which does all the packet processing, whereas the user space consists of applications which make per packet decisions or collect the information from the kernel and send it out to the cloud via telemetry. Several mechanisms exist that facilitate the communication between the kernel space and the user space. The first one is the input-output control, although known as IOCTL. It is used by the EthTool utility for configuring the hardware, and IOCTL uses predefined data structures which can be modified for adding new functionalities to the utility. However, these data structures are difficult to interpret and extend and may result in non-backwards compatibility of the newly added functionalities. Second is proc file systems. It is utilized by the Athros ATH9K and ATH10K drivers for debugging and reporting statistics. Proc file systems reside in the main memory and usually remain empty until when requested by the user space application for reporting the statistics. However, the main shortcoming of the procfs is that it is non-programmable. For example, Athros debug fs provides all the register values and does not allow to specify only a list of registers that we are interested in. The third type of kernel space and user space communication mechanism is netlink. Netlink is a socket-based mechanism, and unlike procfs and IOCTL, which can only be initiated by the kernel space, the netlink can be initiated by both the kernel space and the user space. Also, netlink provides message queues that enable asynchronous communication. That is, the receiver end can process the information at its own schedule, unlike IOCTL and virtual file systems. Finally, netlink mechanism allows multicast messages. Hence, several user space utilities can utilize the information sent by the kernel space simultaneously. MonFi is divided into two components, which is the controller and the collector. The collector is the kernel space component of MonFi that is responsible for collecting the data and measurements from various parts of the networking stack. The collector is implemented as an extension to the driver, thus it shares the same set of functions and data structures as the Wi-Fi driver. It also exposes a set of APIs via which the user space modules can obtain network statistics via netlink. Next, let's try to understand the inner workings of MonFi and how it obtains measurements from various parts of the networking stack. Starting off with the network statistics from the 5-layer and the MAC layer. Wireless NIC provides input-output memory regions containing registers, and these registers are the primary mode of communication between the driver and the NIC for configuration and obtaining their internal status. Functions such as IORead32 and IOWrite32 along with the memory address of the registers are utilized by MonFi to get or set the status of the registers. For example, for interpreting the amount of activity on the channel, airtime utilization metric is used. And airtime utilization is basically the amount of time the NIC senses activity on the channel out of the total time elapsed. Hence, the collector uses the IORead32 function to obtain the register values for the corresponding registers and relays these values to the controller. As each station and access point link is unique and highly dynamic based on the location of the device or the antenna characteristics of the device, MonFi also collects the data corresponding to each associated station. Sample metrics that are unique to each link are RSSI and MAC layer retransmissions. The MAC 802.11 module in Linux systems acts as the MAC layer management entity and keeps a list of associated stations in a data structure called net_device. Also, the Wi-Fi driver, for example ATH9K, contains a data structure called ATH_softc that maintains statistics about each device in the network. The collector uses these data structures to obtain the information about all the stations in the network and report them to the controller. Linux introduces rich set of queuing disciplines, although known as queue disks, between the network layer and the MAC layer that facilitates traffic control and shaping. The efficiency of queue disk layer depends on the packet scheduling method, the size of the queues, and the rate of incoming traffic. For example, if the queue sizes are smaller, the queue disk layer will not be able to absorb the bursts of incoming traffic and it would lead to packet drops. If the queue sizes are longer, it would result in unwanted network queuing and cause large delays and degrades in the performance, although known as buffer bloat. We have modified the QDisk kernel modules in the operating system such that it reports the number of packets currently enqueued in each of its subqueues, and collector relays this information to the user space module. Most modern computation platforms uses shared multiprocessor architecture that consists of multiple physical processor cores, each containing multiple logical cores capable of executing multiple threads concurrently. The operating system schedules user space threads, software, and hardware interrupts evenly to be served by any of these processor cores. Hence, the execution of background tasks and user space daemons such as applications that make per packet scheduling decisions based on the network characteristics can impact the functioning of MonFi. In order to reduce the impact of other processes on the operation of MonFi, we dedicate resources for the operating system, MonFi, and the wireless driver. We isolate logical core 1 and logical core 2 for the operation of the operating system and other user space processes, and dedicate logical core 2 and logical core 4 for the MonFi and the driver operation respectively. First, utilizing the isol CPU kernel boot parameter, we isolate the physical core shown here as PC1 for the operating system and other background tasks, and dedicate the physical core PC2 for the execution of MonFi. Then, using the task set system call or the shed_affinity function, we bind the execution of the controller with logical core 2. And similarly, we bind the execution of the Wi-Fi driver with the logical core 4. As the controller is an extension of the driver, it will run on LC4 as well. Finally, we restrict all the hardware interrupts except the ones initiated by the Wi-Fi NIC from being scheduled on PC2 as follows. First, we obtain a list of all the components that can generate hardware interrupts from the interrupts proc file and then set the SMP affinity of all the components except the Wi-Fi subsystem to LC1 and LC3. Similarly, we bind the SMP affinity of the interrupts generated by the NIC with LC4, thus ascertaining that all hardware interrupts will be scheduled on the logical core 1 and 3 and the hardware interrupts generated by the NIC will always be scheduled on LC4. MonFi provides 3 modes for data collection according to the application on hand. First is the polling-based measurement collection mode, where the controller sends the measurement collection parameters such as the list of measurements to be collected or the sampling rate to the collector, and the collector will then collect and send the measurements according to the specified intermeasurement interval. MonFi also allows to set a threshold. Only a selected measurements will be reported to the user space. For example, if the change in the measurement since the last sampled value is above a certain threshold, only then it will be sent to the user space controller. This helps in reducing the computational overhead of MonFi when there are redundant measurements due to relatively less dynamic wireless environment. Polling-based measurement collection is particularly useful in monitoring the Wi-Fi networks. Next is event-based measurement collection mode that collects statistics only at the occurrences of events. For example, whenever a packet was received or whenever a packet is transmitted, the measurements are collected and reported to the controller. This mode is useful in applications that require measurements for per packet decision making or whenever an event occurs. The third mode is the hybrid mode for measurement collection, which combines both polling-based and event-based mechanisms. In hybrid mode, the collector continuously polls the measurements at regular intervals specified by the controller and stores the measurements in a circular queue. On the occurrence of an event, last n measurements are sent to the controller. This approach is useful in applications that involve time series analysis and neural network algorithms such as LSTM. MonFi primarily uses a netlink for communication between the controller and the collector due to its advantages as discussed earlier. To enhance the performance of netlink even further, we establish a memory mapped region for the netlink's receive and transmit buffers, and these shared buffer prevents the overhead due to data copy. We call this mechanism as MonFi with memory mapped netlink, or in short MonFi MNL. We now present the comparison of IOCTL, ProcFS, netlink and memory mapped netlink. The results show that compared to MonFi MNL, The highest measurement collection rate provided by debug FS is 22% lower and the processor utilization is 20% higher. We then evaluate the impact of user space daemons on the performance of MonFi NL and MonFi MNL. When increasing the synthetic processor load, the performance of both MonFi NL and MonFi MNL drops without using the dedicated CPU resources, whereas it remains relatively stable when using dedicated CPU resources. We then evaluate the impact of network load on the measurement collection rate. When increasing the network traffic, the performance of MonFi MNL when dedicating resources remains relatively stable. Hence, using dedicated cores is necessary to ensure deterministic monitoring rate in presence of network traffic. In this talk, we presented MonFi, which is a tool for collecting Wi-Fi measurements across the networking stack. We first evaluated several kernel space and user space communication mechanisms, and then discussed about the implementation details of MonFi. We also discussed about stabilizing the operation of MonFi under the presence of interfering loads by isolating CPU cores. Our empirical evaluation showed the higher sampling rate and the processing efficiency of MonFi compared to other existing Linux tools. I'll be happy to answer any of your questions, and thank you for listening.